And as usually, we're gonna have a slot of 1 hour and 30 minutes, and you can occupy 45 minutes to 1 hour, and then we'll have 30 minutes to 45 minutes of question and answers. Okay.
Great. Okay. Well, thanks very much. Thank you for inviting me. It's a pleasure to be here after such a long time and to see many people, old friends, but also come back to basically tell you something about the research I've been doing, but also some sort of secret parallel interest that I still have in metaphysics. And since this is, if I'm not mistaken, still the work in progress seminar, I guess. Okay, good. I can.
For some of the speakers, for some not, but still, yeah.
I can pretend this is completely work in progress, so you can tell me, you can help me develop it better. And so yeah, the idea is that here I would like to try to connect two of my passions. One is a passion for metaphysics, and especially metaphysical questions about the composition of objects. And the other one is my passion for consciousness, and also my current obsession for IIT, which is one of the main leading theories of consciousness. So all these brought to the idea to try to put the two things together and try to address the problem of special composition based on some considerations coming from metaphysics and some considerations coming from IIT. So first of all, what is the special composition problem? Well, the special composition question has been formulated by Running Wagon as the question of when does a plurality of things compose one thing, some other thing. So when the parts get together to form a whole, and this is a very old problem. It probably started with Aristotle, probably before that. But in general, in the history of philosophy, there have been three main, let's say, views or ways to approach the problem, or actually three main answers to the special composition question. The first one is nihilism, the view that says that special composition never happens. The idea is that only atomic simples exist, only mereological simples exist, and everything else is just an aggregate of these atomic simples. So this view has some problems. Some people say, well, it's too restrictive because it doesn't reflect at all the way in which we understand the world. Like, there's no tables and chairs, there's no people, there's no cats and dogs, there's just fundamental physical entities. And this is very counterintuitive. On the other hand, it is also likely false, because if we tried to actually explain every macroscopic or mesoscopic phenomenon based on mereological simples, well, we would be in trouble. Like, recall Hazok Chang's talk last Tuesday and his issues with Legoism, the idea that even in fundamental physics, you can't really explain something like an atom as the mereological composition of some parts. There's always something that when you get to the level of the atom seems to be unexplained in terms of its components. So nihilism doesn't really fit and or explain what we observe. On the other hand, there is universalism, which claims that special composition happens all the time, always actually. Every time you predicate something of a set of arbitrary parts, you are predicating something of a genuine existing entity. So the set of all the cats on planet Earth, well, it's a thing. The set of all the tails of cats on planet Earth is also a thing. And this is, on the other hand, too permissive. It's uninformative because then we don't trace any border. And it is also very counterintuitive because we think that some wholes seem to be privileged. That is why restrictivism, which is the third option, is, well, I think has been the holy grail of philosophy since Aristotle, because it says that special composition happens, but only sometimes, according to some criteria. And the advantage is that this is less controversial, that some things are special. On the other hand, the problem is that it has been really hard to find an objective and uncontroversial criterion for special composition. There has been some attempts. I'm not going to try to summarize the history of special composition here because I'm, of course, like, you know, also way better than me some of the attempts, but in general, one of the lines of research that go across really the centuries and the millennia is the one of hylomorphism, where again people like Aristotle started thinking that we can explain special composition because some wholes have some special property, for instance form and matter in his case, and then Van Inwagen building on this hylomorphic kind of framework claimed that in particular biological organisms are special cases, and composition happens at the level of biological organisms, again because they have some sort of special property. And then more recently, Jaworski and Marmodoro argued in terms of causal powers that wholes can be characterized by either individual making structure of causal powers or structure versus substantial powers in the case of Anna. And then there's many other views. I'm not going to give an exhaustive list here. What I would like to stress is that the idea in general has been that maybe we can characterize special composition, meaning we can characterize wholes in terms of their causal powers, and in terms of the fact that they seem to have causal powers that are not reducible to the causal powers of the parts. So this is one of the basic ideas that have been pushed for a long time. What I would like to do is to try to give an account of restrictivism, to actually propose some criteria. And I called it a principled account, maybe a little bit over ambitiously, because, well, it seems to me we have to start from first principles in such a complicated matter. And I have in mind at least two types of principles. One kind is metaphysical principles. So we can start from considerations about causal powers and why causal powers seem to be really important when we try to deal with what exists and try to explain what exists. For instance, the eleatic principle. And then some phenomenological principles. For instance, the fact that there are some properties of experience that for us represent maybe one of the few sources of evidence about reality. So if our experience is in one way, there must be a reason, and we can try to use phenomenology to then look into the physical world and try to find if our phenomenology is informative and allow us to understand something about the physical world which is out there. So this is why it is principled. And so the proposal is very simple, as I said, it's not new, nothing original, nothing revolutionary. It's something that in the debate of emergentism and hylomorphism people have been saying forever. The idea is that special composition happens when a whole, meaning a system of elements, has causal powers that are not reducible to the causal powers of its parts, meaning the elements that constitute it. So it is very simple. The question is, how do we define causal power? And how do we check for reducibility? And how do we validate this hypothesis? Do we have any objective case in which special composition happens so that we can say, yes, our explanation succeeds because we correctly account for composition in this case? Well, if these are the questions that you have been always interested in, you are in luck, because this is exactly what I will do today, right? I will use integrated information theory to solve this problem, and in particular, I will try to define causal power in terms of information, irreducibility in terms of integration, and for the validation of this hypothesis, I will try to use the case of consciousness and the case of life. Two cases that are pretty relevant, and people have been using these cases for a long time to basically argue that something like restricted composition, a special composition, must happen. And I will stand just because so you can see better. Okay, so the first question, oh, by the way, please interrupt me anytime. I will go through some examples because I really want to try to talk to you as metaphysicians, trying to tell you why I got interested in the information approaches to consciousness, but also why I think it's relevant. If you don't understand something, please ask me. I'm not super familiar with some of the things I will talk about, so please ask me any clarificatory question. If you have discussion or knockdown arguments, maybe we can leave them for the discussion.
So just a very quick clarification question. You're using SC, I think you said special composition.
Yes.
So I'm sort of saying special composition happens when... What's
Yes.
the difference between composition and special composition?
Oh, there's no difference.
Okay.
I'm just saying, so special composition is this idea that a whole exists as one. So, like Van Inwagen.
So I thought Van Inwagen distinguished the special composition question from the general composition question.
Well, I'm talking about I'm using special composition just to say whenever something constitutes a whole.
Okay.
General composition, I mean, you could say, for instance, that something can be composed of parts even if it doesn't have emergent causal powers, in the sense that we can talk about something as being an aggregate but without having causal. Is there something different from, like, for instance, the Van Inwagen?
Yeah, that clarifies.
Okay. I mean, it would be helpful if then you clarify, because okay. So anyway, but is it clear what I'm after? Okay, good.
If we just read composition,
It's better to just stick to composition. Okay. So first step is, how do we define causal power? And one idea that has been proposed in the past is that maybe causal power has something to do with information. Now, I disagree. We will see why. But let's go one step at a time. So let's imagine we have a little system, which is just a toy system with two units that perform Boolean functions like logic gates. We know nothing about these units. We don't know what their function is. We just see that they are connected in some ways. They have self loops and they have a connection between them. And what we do, we observe that every time they are in the past in state 0, 0, in the present they are in state 0, 0. And every time they are both on, in the present they will be both on. So they are either both on or both off. Information theory people have developed different ways to try to measure and quantify the information that we can get, let's say, from observing something like this fact, like a correlation. They are always either off or on together. And one way is to use what is called effective information. I will not comment on the formulas. I'm not a mathematician. I don't know these complicated things. But the general idea is that if we take the probability distribution of A and B being in state 0, 0 in the past, knowing that A and B are in state 0, 0 right now, if the system is what we have observed, we can infer that, the probability of AB being in state off in the past is 1. Now, this is only for the state off. What we can do to try to ask ourselves, well, knowing that AB in state 0, 0, how much information conveys about the system? Well, we can compare this probability distribution with the probability distribution of the system if there was absolutely no correlation between the states. So this is what is called max entropy or uniform distribution. If we observed that every time AB is in state off, at the previous time step, anything could really happen. It could be that AB was off, or A was on and B was off. If we see that every state can lead to this state, and we have no idea where this came from, we would infer that this is a random system. But in this case, it's not. Very consistently, we find with probability 1, AB was in state off, if it is now in state off. So we can use effective information to measure the relative entropy, so the distance between these two probability distributions. It doesn't matter how. One way is to use Kullback-Leibler divergence, another one is to use Earth-Wilker's distance, but we can quantify the difference between these two probability distribution in bits, and we can say that knowing that AB is in state off gives us 2 bits of information. for instance. Trust me on this, we can talk more about that if you want, but it's not important. But now there's a problem. We could have two systems that look the same, and the observed transition probability matrix, sorry I didn't say what that was, this is a transition probability matrix, it's basically state of the past and state of the future. They have the same TPM, observed TPM, and so they have the same effective information for one state, off. However, there is something that we are missing that we could see if instead of only focusing on the information we can get by observing the system, we focused on what we can get if we perturb the system. And this has been explored at length in the interventionist approach to causation and information, perturbational approach. So what we can do is we can say, well, if I try to expand my TPM to all the possible states that the system can actually reach, which means if I try to perturb the system in all possible states, what I observe could be that actually the system does different things. So in one case, for instance, my system, when it is in state 0, 0, will go in state 0, 0, and 1, 1 will go in state 1, 1. But when only one of the two nodes is on, the system will go in state 1, 1. On the other hand, the same looking system, when only one of the two nodes is on, will stay in state 0, 0. So by perturbing, we can say that we can disentangle or sort of understand what a mechanism is independently, or at least above and beyond what a mechanism does. So we can understand, for instance, that these two little gates are OR gates. They turn on whenever at least one of the inputs is on, wherever these gates are AND gates. They turn on even if all of their inputs are on. And we can see this only if we perturb. So why am I saying that this is a way into what a mechanism is and not what a mechanism does? Well, because if we had in front of us a mechanism, or like a system of mechanisms that is in the all-off state for the entire duration of the universe, well, we would know what it does nothing, but we wouldn't know what it is. It could be this system or this system. And if you think about it, this is already something that is related to the notion of causal power. First of all, because we are trying to say, well, this system, if it is in the off state, is not doing anything, but it could turn on if only one of the two inputs turn on. So we can use the counterfactual analysis to say what the powers of this system are. And this system has different causal powers. It would turn on only if both inputs were on. It's a little bit like saying, classical example, the glass is fragile even when I don't break it, because it is what it is. In the physical setup of the glass, the truth makers are there to say that the glass could shatter if I were to strike it or break it or whatever. So perturbation is important to get to what things are. This is one of the claims that in the philosophy of information and causation has been already argued for. However, there's also something more that you can learn from perturbing. And we can imagine, again, we have two systems. These are different systems. Again, we don't know what they are. And again, they have the same observed states. They are both off and both on together. But then when we perturb, we could find out that these two systems have the full TPM, the difference in these ways. So this guy here goes from state 1, 0 to state 1, 0, and this guy from state 1, 0 to state 0, 1. So what can we infer from observing those TPMs? Well, we can observe that these are actually all the same gates. They are all copy gates, but their connectivity is different because these two guys are copying themselves. They are staying in the same state where they were, whereas like these two guys are copying each other, so their state flips, something like that. So what we can do is to use perturbation also to check not only what mechanisms are, what the causal power is in the sense of what they are, but also how they interact with each other, the causal constraints between the elements or the parts of the system. So we can infer that the causal model of these two systems is actually different. And even if we observe that there are connections, well, it doesn't mean that the connections are actually doing any job. They might be pure noise, or simply the weights might be so low that they don't actually make a difference. There is, however, one question, which is, this is all fine and we can learn a lot from just perturbing, but it is hard to quantify exactly what we are losing and how much information there is, because we've seen that effective information stays the same. And also there is no methodology to actually say, whenever we perturb, we can observe a difference in the TPM, but what do we do with that? Do we just infer what the system is? Well, we can say something more. So one proposal is to use integration, meaning cutting, and I will tell you in a second what cutting means in this case, to check whether these systems have the causal constraints between their elements that we can infer from the TPM. So if we have the TPM of these systems, what we can do is to try to compare the information that is generated by knowing the state of the system as a whole to the information that is generated by the system considered as parts. So what we can do, for instance, in the first case, we can compare the fact that if we know that the system AB is in state 0, 0, we know that in the past it was in state 0, 0 with probability 1, with the fact that if we know that only A is in state 0 in this particular system that has a self-loop, we also know that A was 0 for sure in the past. And this is also true for B, because basically they don't talk with each other, right? So what we can do is we can compare the probability distribution of the system as a whole with the, I guess this is called a tensor product of the probability distributions of the parts, and we can find that if there is no difference between the reconstructed probability distribution and the initial probability distribution, we can say that the information generated by the system as a whole over and above the information generated by the parts is 0. And we call this phi, integrated information. So this is already one of the measures that integrated information theory tries to apply to this kind of systems. So again, the effective information of state 0, 0 is 2 bits, but in this case we can see by pretending that we are sort of cutting this connection and considering the two systems as, the two elements as two separate parts or as two separate systems, we can figure out that it makes no difference. This cut makes no difference to the way in which we can predict the state of the system. So in this other case, however, the cut makes a difference. If we imagine that we disconnected these two guys, we would find out that based on what we know about A being off, the probability of A being off or on in the past is completely a chance. So it's 50% probability that A was on or off, because we basically have ignored the connection from B to A. Another way to conceive of cutting is noising. So we can pretend that this connection is a noisy connection. We are basically trying to say, what is A doing? How am I able to predict what A is going to do or was doing if I completely ignore so independently from what B was doing or is doing? So in this case, we can see that if we take the initial probability distribution of the system, and if we take the product of the two probability distributions of the parts, and we combine them together, then what we find is that these probability distributions are not the same. We can compute this difference with integrated information, which is a similar sort of like elaboration on effective information, and the idea is the same as before. We can compute the relative entropy, the distance between these two probability distribution, and we can find that integrated information in this system is not 0. Let's say it's 2. One thing that is also worth mentioning, I think, is that if we take this, if we take systems where we really don't know even if the connections are there, or the weights or anything, we can use integrated information, that we can use cutting also to understand whether a system, like a connection between two elements, is actually a causal connection or not. For instance, in this system we can observe that these two elements seem to behave in a consistent way, so they are correlated, the states are correlated. However, we know that if we cut this connection between the two, nothing happens, because we can do the trick where we compare probability distributions and phi is 0. So what we can use this fact for is to ask ourselves, well, maybe we have to look somewhere else. Maybe there's other elements around that are actually explaining why A and B correlate. So we know that there's no causation between the two, or at least we can infer that probably there is no causation, but there might still be correlation. So integrated information is a nice way, I think, to talk about causal interactions between things, and in a sense also to figure out what are the causal powers of a system that are not reducible to the causal powers of the parts. Simply because if we take the parts and by joining the probability distributions together we don't find that anything is missing, then this means that really the system is not a system, it's just an aggregate of parts. Okay, so what does in general integrated information say about a system? How do we try to characterize a system in its sort of entirety? Well, the idea is that when we take a system, it doesn't suffice just to try one cut, or just to say, I want to know if A, B are a system. What we have to do is we have to perturb the system in all possible ways, and we have also to cut the system in all possible ways. And we have to measure integrated information for all the subsets, for all the cuts, for all the perturbations. And this is what in IT is called unfolding, meaning unfolding the substrate, meaning just giving a complete causal analysis, and it is represented in some sort of weird thing called cause-effect structure, where you have all your repertoires of each individual subset of the system, you have all the small phis, you have all the integrated information, and then there are a couple of considerations that should be made to understand how do you actually treat all the possible subsets, and where do you find the one that is really your whole. But maybe we can talk about that in the discussion.
Sorry, Matteo, so do you do this with neurons?
I'm gonna get there. Oh. Thanks. So one thing that IT has been famous for in the past is this idea that there is one number phi that quantifies, well, consciousness, but also, if you read any of the papers, phi is also supposed to quantify the intrinsic cause-effect power of a system, meaning the irreducible causal power of a system among itself, so upon itself, so all the elements, how they constrain each other in a system. And you can think about this as an operation of summarizing all these causal constraints and all this integrated information into one number that reflects how much a system is integrated. So far, I don't know if I managed to actually convey the idea that we can use information and integration to try to check whether a system of elements is not only, well, their activity is not mere correlation, but is actually causation. There are causal interactions, and whether the causal interaction and the causal constraints of the parts are sufficient to explain the causal constraints of the whole. IIT says that if there is information and this information is integrated, then the whole has causal constraints that are not reducible to the causal constraints of the parts. So this was, so to speak, the metaphysical side, in the sense that I think from considerations about causal power and from consideration about unity and wholes and irreducibility, and via the use of information and integration as tools to check for information and integration in, well, clearly simple systems and abstract systems like systems of logic gates, we have one way, at least one candidate way, to check for irreducible causal powers. Now, the question that I wanted to also try to address is whether we can also validate this hypothesis. I mean, this sounds very cool, but how do we know if we check on something, on an object like a chair, how do we know whether this explanation actually gives the results that are correct or that we expect or not? Well, there are two cases that I think we could use, and this is very controversial, to try to validate this approach. One is starting from consciousness. So now this is a very strange way, I think, to try to connect consciousness to the metaphysics of composition. The idea is the following. If it is true that we can doubt about the external world existing and causal power existing, we know nothing about what's out there in line with Descartes, but something we cannot doubt about is our own experience and the properties it has, we could try to use the fact that our experience is both differentiated and integrated, like unified, to make the following inference. Well, if my experience has these two properties, it is always unified, meaning in this very moment you are hearing my voice and you are looking at the screen and seeing pictures, there must be a fact that explains why the sound and the colors are part of the same experience, whereas like your blood pressure is not, even though your brain is probably monitoring also that, or your breathing was not until I said, and maybe now you're noticing that you are breathing right now. So there must be a fact, and what we can infer is that since we know that the brain is probably the place where it's the most important place for consciousness, we can infer that the substrate of consciousness, whatever that is, will also be differentiated and unified, meaning it will also have differentiation and integration. So the idea is that somewhere in the brain there might be a border that is an objective border, because it is objective, the fact that my experience has some content that is unified. And the hypothesis is, well, maybe we can use these considerations that come from metaphysics about information and integration, which also, by the way, apply to experience, according to IIT, to check whether in the brain there is something that satisfies this criterion for composition as an object. Okay, so in what remains, I think I have 15 minutes. Any questions? No? Maybe? No?
Later.
Okay. So in the time that remains, I would like to give you these two examples, one about neuroscience and one about life, to try to say, well, maybe we can try to apply this method and check whether any idea about information integration applies to two examples that have been quoted as paradigmatic cases of composition. So life, since Aristotle was really one of the motivations of trying to come up with this hylomorphism thing, and consciousness more recently is another one. So the brain is an interesting object because it is kind of handy, the fact that neurons fire. So we know when there is a difference that makes a difference, we observe something very clear. As I said the other day at lunch, it's not that if you heat a neuron of 0.00001 degrees, yeah, maybe that might make a difference to some molecules or whatever, but the main difference for a neuron is whether its inputs are above the threshold and the neuron fires. And we can observe that. We see neurons firing easily. We can record that. So this is good. If I had to check what's the difference and makes a difference for a chair, I wouldn't know where to start. So that's a little tricky. So we can wonder, is information important for consciousness? Since we know that consciousness might be a good way to check whether there is composition that happens in the brain, both information and integration should be important for consciousness. Well, what we know is that we can conceive of information in the brain, especially of high degrees of information in the brain, if by perturbing the brain in different ways, we find that the same perturbation leads to the same result, and different perturbations lead to different results. So there is differentiation between the states of the brain, and consistently one state leads to the other. So this is something that it's very important. So from observing the result of perturbing the brain, we can infer that there is a differentiated connectivity and that there are some constraints between the different elements that are non-random, merely correlational. Actually, at this stage, we might still be dealing with correlation, but there are at least sign of high information. What happens when we have low information in a system or in the brain? Well, the opposite, meaning that two perturbations of the same kind might lead to completely different states, and different perturbations could lead to the same state as before, so there's really no connection between one state and the other state. This, of course, oversimplifying, but this is also a brain of just 6 nodes, so it's pretty easy. So the idea is that we could infer that the interaction between the elements, it's really noisy, it's really random. There's not a lot of information. We cannot predict based on one state that is observed the next state or the past state, and there's not really a lot of causal constraints between this, the state of the individual elements. What we know is that if you try to measure information in the brain, high information is usually it correlates with high levels of consciousness, meaning the activity of the brain is differentiated. However, there are states in which information is very low, meaning the different state of the part of the elements of the system don't really correlate or have much to do with states of other parts of the system, and this happens, for instance, during epileptic seizures or during anesthesia. But again, as we said before, this is not enough, because information, pure information, even if we are perturbing at this state, is really just correlation. It is not causation, because we do not know whether by cutting the connections between these elements we would find that they still do whatever they were doing. So we have to check for integration too. And what does it mean to have high integration in the brain? Well, it means that if we partition the system in different ways, there is no way to partition the system that doesn't have an effect. If I observe this state and physiologically the brain entered in that state, but then I observe the same state and I cut or noise or partition, whatever that means in the brain, I do always observe an effect. Then I can infer that the system is integrated, has high integration. If I partition my system and I observe consistently that the same state leads to equivalent states, so my partition doesn't make a difference, then what I can infer is that the system is indeed not integrated. I am actually not messing up with relevant and vital and crucial connections. Again, this is also true in the brain, and this also correlates with consciousness. When we have high integration, a stimulus that I receive in my eyes will affect my occipital cortex, my visual cortex, and there will be some effects that travel the entire cortex and will affect my frontal lobes and my temporal lobes, so the whole is really integrated. If I have low integration, like in deep sleep, for instance, where there is a breakdown of cortical connectivity, whatever happens in one part of the brain is not able to affect long range, so it doesn't have long range functional connectivity, and it will stay local. So integration is disrupted in states like deep sleep or anesthesia. However, only integration, again, it's not enough, because we could say only integration without high information is not good for complexity either. I haven't really elaborated on this, but the idea is that they go together for consciousness and likely also for composition. So this is all, again, all good. We have evidence that if we try to estimate information and integration in the brain, it correlates with consciousness. But can we do something even more practical, more pragmatic? Well, yes, we can. We can try to apply complexity measures to the brain, like in vivo, online, on a patient, or on a subject. However, there's two different ways to do it. In the past, and still right now, the majority of complexity measures are applied on what is called spontaneous activity, meaning we just observe what the brain is doing, we record it with EEG, we try to feed it into something like a complexity algorithm that is doing something like the WinZip thing, like the metaphysicians complexity. Basically, the idea is that if a signal is complex, it will be very hard to compress. If a system is very redundant, if I have 1 million ones, I can just tell you there's 1 million ones. It's a short string. I don't have to tell you 1 million times 1. So it's very compressible. If I have, I don't know, pi, well, that's a different case. But if I have a non-periodic number, well, then I have to tell you all the digits of the number. So it's very hard to compress. However, there's a problem. If we just use the spontaneous activity and we feed to our complexity compression algorithm pure noise, well, the algorithm will think that pure noise has high complexity, because pure noise is very hard to compress. If we feed it a very informative scene, like, I don't know, the Andromeda Galaxy, whatever, with a lot of stars and stuff, the complexity will still be high. So we are not able to disentangle these two cases, because the measure of complexity is basically channel information. It's just this kind of complexity. So one solution that is very much in line with what I've just said so far is that maybe if we use perturbation, we can actually get a better estimate of the complexity that is interesting, which is integrated information. And the idea is that if I have two signals and one is pure noise and the other one is very complex, if I just try to compress it, they will look non-compressible. However, if I try to perturb each of these two systems, my perturbation will not have an effect in the system that is purely random, because the fact that I turn on this guy will not affect the other guys. The other guys are still doing their random thing, right? Whereas if I try to mess and perturb a system that is not random, that is differentiated, then taking into account my perturbation, I will observe a difference, and I will know that the complexity that I observe in this system is not due to noise or chance. So if we use something like perturbation and complexity index, we can distinguish these two cases. The complexity algorithm will give low complexity, perturbational complexity to this system, and high perturbational complexity to this system. What has been done is try to do this with a real brain by stimulating the brain with magnetic, transcranial magnetic stimulation. So when the person is awake, you use transcranial magnetic stimulation to zap the brain, a very specific part of the brain, and then you use high density EEG to record the response of the TMS in that specific area of the brain, and you observe how far it travels in the cortex and how much it lasts in time. So you have all you need to then get a measure of complexity. So you try to squeeze all this in the algorithm that tries to compress the signal, and then you have your perturbational complexity index, which takes into account the perturbation. So super quickly, what has been found is that by doing this, we can create a scale called perturbational complexity index, in which we start from the cases where we know that the patients were awake, and they also immediately they were able to report that they were conscious and they were doing things or experiencing things. And these are all perturbations in PCI, and they've been arranged according to a value. So 0.8 is the maximum, and the threshold, I think, is around 0.4, 0.45, something like that. And then they tried in this paper by 2016, these are collaborators of Tononi and Massimini, they tried in cases in which we have no report, but we know, based on neuroscientific evidence, that people are either in deep sleep or they are under different kinds of anesthesia, midazolam, xenon, propofol. And what they found is that, well, people didn't report they were conscious in that moment because they were asleep or anesthetized, and the level of PCI was below a certain threshold. They didn't, of course, decide a priori. They actually marked the threshold based on the data. And there is a last little section that is very interesting, which is the green dots. So they tried to do exactly the same thing, but on subjects that were either in REM sleep, meaning they were dreaming, or they were under ketamine. And we know that ketamine is a tricky anesthetic. Well, interestingly, the value of PCI of these people was very similar to the one during wake, sometimes indistinguishable. However, after they were woken up from REM sleep or they recovered from ketamine, they could report that they had some experiences. So here there was no report at all, not even delayed report. They were waking up from anesthesia and say, I wasn't there for half an hour, I don't remember anything, I wasn't experiencing anything. Here we have people saying, no, I was dreaming, I had a complex dream, or I was tripping hard under ketamine, there was like a lot of interesting things happening. But of course on the spot, you would have said, well, no, that person is completely unconscious, it's unresponsive, it's unconscious. So PCI seems to discriminate very neatly this people from these people. So these are all physiological states, physiological or induced states, non-pathological states. But of course, this method can be also applied to move to the gray area where we cannot even use behavioral responsiveness or delayed report to check whether people are conscious or not. So what they did, after they sort of validated the scale of PCI on the previous studies where they could check whether somebody was asleep and whether they were able to report even after the experience, they applied the same measure to patients that were in these states, which are pathological states called disorders of consciousness. MCS is minimally conscious state, VS is vegetative state. So vegetative state is like after coma, people are unresponsive, we don't really know if they are even experiencing anything at all. What they found with the PCI value is that most of the minimally conscious state patients had levels of PCI that were in the lower sort of spectrum of the wakefulness values. And some vegetative state had, well, most of the vegetative state patients diagnosed vegetative state based on behavioral assessment were below the threshold that was in the same range of deep sleep and anesthesia, but some vegetative state patients actually had some values of PCI that were compatible with wakefulness. And this is an interesting case, has a lot of medical and ethical implications and on the diagnosis. So, this is jumping around a little bit, but what I'm trying to convey here is that if we start from considerations about causal powers and irreducibility, and we think that we can use consciousness as one example just to validate our method, in which we say, if I am conscious and I am experiencing unified content, then there must be something in the brain that is unified and that is a whole, that is not reducible to the parts. So the idea to use neurophysiology and the perturbational approach and PCI is to say, well, maybe the full neural correlates of consciousness, which is really the part of the brain that seems to correlate with the presence or absence of consciousness, maybe that could be a paradigmatic case of a whole, in the sense of a compositional whole. And IIT has tried to develop ways to actually check in the brain where the major complex, what they call major complex, which is this sort of the maximum of integrated information, could be. The current hypothesis is called posterior hot zone hypothesis, in which the parietal, occipital, temporal lobes seems to be not only more important for consciousness, but I think more interestingly, they seem to have the type of architecture that is able to support the higher degrees of phi. So, for instance, we know that all the sensory cortices have grid-like architecture. They have elements that have lateral connections. They are very much integrated with sort of nearest neighbor connectivity, and these grids are connected with each other, whereas the frontal lobes have more of a random connectivity, which might be very useful for other purposes, such as reasoning or whatever, control of behavior, flexibility and learning, but they might contribute less to consciousness because they are less able to integrate information. And of course, there are a lot of predictions on what will happen if the major complex shrinks because of some lesion, or it moves because of massive lesions, or it is split because, for instance, in the split brain case, the two hemispheres are separated, or if there is some functional splitting, or a lot of interesting and weird cases. So this is the way that, in a sense, independently, cognitive neuroscience is trying to find the neural correlate of consciousness, and I think, my claim is that maybe this can be used as a paradigmatic case for composition. Well, I'm not going to talk about a lot, also because it's not my field of expertise, but since I know that you're very interested in the problem of life, I wanted to just mention a couple of things. Again, to me, life is a little bit maybe a less powerful argument, because we don't have direct, so to speak, evidence like we have for consciousness that life is unified or composition happens. However, we have strong intuitions, right? As I said, probably Aristotle started thinking about composition by realizing that animals do things that rocks don't do. So life seems to be a very good case to validate our criterion. If it doesn't apply to life, then maybe, I don't know, maybe we discovered something else, or maybe our intuitions were mistaken. That's an open question. But what I want to just, maybe this is only a little teaser, really. What I wanted to bring to your attention is that a couple of years ago, this paper has been published by Sarah Walkers, William Marshall, Tononi, Albantakis, people from the Madison lab and people from Arizona, where they basically tried to apply the integrated information analysis to a Boolean network model of the fission yeast cell cycle. So the idea is to get, this is from the abstract, I just wanted to read a couple of statements that I think are interesting and might maybe spark your interest in reading the paper. They say this, they demonstrated this biological model features a non-trivial causal architecture. They show that some specific properties of this underlying causal architecture relate to the biological notion of autonomy. And then they suggest that this kind of analysis, so the causal organization of a system, including these features like intrinsic control and stable causal borders, could provide, should they say, relevant, they should prove relevant for distinguishing life from non-life. So what do they actually do? Well, they take the 4 phases of the cycle of the fission yeast cell cycle, and they create a model, a Boolean network model, and they say that it reproduces the protein expression states through each of these 4 phases, and also they basically represent 9 proteins that are known to be key regulators of the cycle. They represent them as nodes, and the links are inhibiting or activating biochemical interactions between pairs of proteins. There's a lot of details, but basically what they do is they represent a Boolean sort of network that is their model, their causal model with inhibition and activation, and they check what it does through 9 time steps. And then what they do is they try to do exactly the same thing I was talking about. They try to say, well, let's take 2 nodes and let's try to see what, knowing the state of these 2 nodes, we can predict about the previous state of the nodes and the future state of the nodes, and then we try to cut away, meaning marginalize or noise in the model, the interaction between some of the nodes and some other nodes, and in the end they try to compute the integrated information for different subsets of this Boolean network, and they discover that there is a network of 8 nodes that seems to yield the highest values of integrated information, but there are also other local maxima of integrated information, meaning some subparts of the system that are not reducible, but they have lower value of integrated information. That was really just a teaser. Maybe you can talk more about that. So, to conclude, the idea of maybe non-special composition, but just composition, has been, well, debated for a long time, and one way to try to approach restrictivism is to give a criterion that allows us to distinguish wholes from mere aggregates of parts. This missing criterion, I think, could be phrased in terms of causal powers and irreducibility, and I am thinking that maybe integrated information theory might actually provide the tools to do this through the notion of information integration. I think one interesting step is how to validate this model, and my proposal is that both consciousness and life seem to be good places to start. So the proposal in the end is that maybe non-special composition, but composition in general happens whenever there is integrated information. And open questions are, of course, well, how much is this model applicable and how much it is generalizable? What would happen if we did this kind of analysis on not the yeast cell cycle, but, I don't know, in the future when we will have a complete causal model of the cells composing, I don't know, C. elegans or a small brain or whatever. What happens if we do it on brains of different animals? What happens if we did it on artificial systems? I will actually go to the last point and say, does this view entail panpsychism? Or does panpsychism become a sort of empirical question? If we checked and we found that tables and chairs don't have phi, but brains do, well, IT would not be panpsychist. It would say consciousness is only in some places, but interestingly, it would also say that composition happens only in those cases. So consciousness and composition will have to probably go together for IT. The last open question that I started thinking about, especially after talking with Hazok-Chan, was this interesting idea of circularity that is not necessarily bad or vicious, but it seems to me that if we want to check for composition, a little bit like if we want to check to assess whether a system is conscious or not, well, we have some problems because we don't really know when composition happens, and we don't really know if a system is conscious from the outside. So what we can do at most is we can find some paradigmatic cases where we validate our method, and then we say, whenever we apply it to other objects, then we have to trust the theory because there's nothing else we can do. We cannot have proof that an artificial system is conscious because we don't have access to the experience of the system. The only thing we can use as an inferential basis is that whatever are the properties that we have good reason to think that at least correlate with consciousness in our brain are instantiated in an artificial system, and then we have to explore whether we have reasons to make the inference that the system will be conscious due to these properties. Is it the same for composition? Is it just a matter of convention and saying whatever we want to define as a whole deserves the name of a whole, and our criterion should reflect that? Or should we have some independent reason to think that some things constitute wholes and composition happens, so that then when we check if our criterion works or not, we can use these intuitions to validate the criterion. And that's it. Thank you very much.